Hello and welcome to the Frontiers of Physics lecture series. Tonight we have Carroll, theoretical physicist from the California Institute of Technology, talking about the many worlds of quantum mechanics. But tonight is a special occasion because it is the first lecture since the tragic death this summer of our colleague, Professor Ann Nelson. So we will start with a tribute to her by Professor Stephen Sharp.
Just hit space. Good evening. My name is Steve Sharp. I'm a professor in the physics department here. And before we start with the lecture tonight, I've been asked to say a few words about the tragic loss of our colleague, Ann Nelson, who died about 2 months ago in a hiking accident. Ann was one of the most highly esteemed members of this university and our physics department, as indicated by her numerous awards, some of which I've listed here. She was awarded the American Physical Society's Sakurai Prize for Theoretical Physics last year. This is the highest award given by the American Physical Society for theoretical physicists. Ann was a brilliant particle physicist who addressed the most fundamental questions in theoretical physics and cosmology. And I do not have the time to go into it. I've listed some of them here. Dark matter, dark energy. I do want to say she liked coming up with nice names for things. So dark energy from mass-varying neutrinos, mavens. She was a maven herself, someone who had deep knowledge of physics, of particle physics. These are the questions that motivate particle physicists, all of us, and cosmologists. And she was good at trying to answer them, better than most of us. She was a master at coming up with theoretical models which could address these problems in a way that led to experimentally testable consequences. So as we say, she was a theoretical model builder, and I would say without peer, worldwide. Ann was passionate not only about physics, but also as a true Northwesterner about mountains and flowers, the outdoors. And here I have a blurry picture from 1992 of Ann there, myself, David Kaplan, who's in the audience on the top of Mount Rainier. We did many wonderful hikes together. She was also passionate about teaching. She was an award-winning teacher in our department. About mentoring. She mentored many students, graduate students, and postdocs to become successful faculty members. And in general, she loved bringing the joy of physics, science, and hiking to everyone. Here she is teaching Palestinian students in the West Bank. In particular, especially over the last few years, she took many concrete and successful steps to increase the diversity and inclusivity of our departments, our faculty, our student body, and more generally our field, exhorting us all to follow and leading us by example. Now, I cannot do justice in this short time to all her contributions to physics, to the field, but I do want to say one of the things that was special about Ann was that despite the fact that in any discussion she was in, she was probably the smartest person, she never betrayed a hint of arrogance. She just wanted to learn, wanted other people to learn, wanted to help them do that. She was a warm, caring person. She was a friend to me for more than 35 years, colleague for more than 25 years. She was just an amazing person. Overall, she was an inspiration to all of us and will be terribly missed. If you want to learn more about Anne, there are obituaries in the Seattle Times, the New York Times, Physics Today, and also the Mountaineers, to show the two sides of her life. Amazing person. So to celebrate Anne's legacy, to honor her achievements, the university has set up a fund for endowing a professorship in physics. The Dr. Ann Nelson Endowed Professorship in Physics, which, as it says here, will support individuals committed to diversity-related work and whose record of research, teaching, and service reflects a commitment to diversity and equal opportunity, and also to excellence in physics. So I encourage you to consider donating to this fund. I assume these slides will be made live, and then you can click on links. Okay, thank you for your attention.
So the goal of the Frontiers of Physics lecture series is to bring renowned scientists like Shan Carroll to give free lectures to the general public on the most interesting and novel topics in physics. We aim to share with you here in Seattle the excitement of physics, how it allows us to describe nature at the most fundamental level, and how it shapes our understanding of reality. The lecture is only possible by the work of the Frontiers of Physics Lecture Series Committee and our benefactors, Dr. Patrick O'Hara and Dr. Katrina Randolph. If you would like to learn more about how to support the Frontiers of Physics Lecture Series, the endowed professorship in honor of Ann Nelson, or become more involved with the department in general, please reach out to me following the lecture or contact the department by email. We host this Frontiers of Physics lecture series about twice a year, and all lectures are filmed by UW-TV and are posted online after the lecture for you to watch and share. Our speaker tonight is Shan Carroll, theoretical physicist at the California Institute of Technology. Shan obtained his PhD at Harvard University under George Field and held positions at the Massachusetts Institute of Technology, University of California, Santa Barbara, and the University of Chicago before moving to Caltech in 2006. Shan is an expert in gravity, cosmology, the origin of the universe, emergent phenomena and complexity, the fundamental nature of space-time, and the foundations of quantum mechanics. He's a fellow of the American Physical Society and has received many honors and awards, including recently the Andrew Gemant Award from the American Institute of Physics and the Guggenheim Foundation Fellowship. He has authored 100 publications, mostly in physics, but also in philosophy, and has published 6 books, including the New York Times bestseller, The Big Picture, and his latest book is Something Deeply Hitting, Quantum Worlds and the Emergence of Space-Time. His contributions to popular culture include consulting for many films, most recently Avengers Endgame, and he hosts the podcast Mindscape. It is my privilege to introduce to you Dr. Shan Carroll.
Thank you. Let's see if this works. Technology. I'm a theoretical physicist, so this doesn't always work. Okay, good. It works. Thanks. It's great to be back here in Seattle at the UW, which is one of my favorite physics departments, one of my favorite places to visit. And I would like to talk about quantum mechanics. I've written a book about quantum mechanics. My publisher says I'm supposed to tell you that when I give these talks. But you are allowed to ask, why in the world would anyone write a book about quantum mechanics? There are enough books about quantum mechanics. And in fact, as part of the research that I did for my book, I went to Amazon.com and I typed in quantum into the search bar, and you can guess what happened. I mean, there's Quantum Physics for Babies, which is actually quite a wonderful little book for the youngsters out there. But there's also quantum leadership, quantum yoga, quantum touch, quantum healing, quantum success. And none of these books are really about quantum mechanics in any profound way. So why is that? Part of it is because quantum mechanics is hard to understand, and therefore it's been sort of misused. It's sort of filtered into the popular imagination in ways that professional physicists would not really recognize. But also it's in part because professional physicists have let the rest of the world down. both in terms of explaining quantum mechanics and in terms of understanding it ourselves. We give people the impression, oh my goodness, there's all these people up there. Hi, people up there. Hi. We give the people, I'll try to remember to look at you occasionally. We give people the impression that not only is quantum mechanics hard to understand, it's impossible to understand. It's fundamentally mysterious. And so I don't usually like to lean on authority for things like this, but since I'm talking not about a fact about physics, but a fact about our understanding of physics, let me lean on this guy, Richard Feynman, who famously said, I think I can safely say that nobody understands quantum mechanics. And whenever I wrote a recent piece in the New York Times pointing out physicists don't understand quantum mechanics, quoting Feynman, and remarkably, only 2 people wrote me saying, what do you mean I understand quantum mechanics perfectly well? Sorry, only 2 professional physicists wrote me in saying that. There's lots of other people wrote in. Of course, it may be true that there are individual physicists who do understand quantum mechanics, but the rest of the field does not think that they understand quantum mechanics. So as a field, we do not understand quantum mechanics as in physics, and that's what Feynman says. And you know what? That's fine. It's fine not to understand things. Science is driven by not understanding things and then saying, well, let's work on trying to understand this. What is not fine is that in the case of quantum mechanics, we haven't done that. Now, we use quantum mechanics all the time. We can use the predictions of quantum mechanics to make extraordinarily precise and amazing technologies. We can discover particles. We can build theories of the universe. We can build lasers and transistors and other applications of quantum mechanics. But we're using quantum mechanics in the way that the typical person uses their smartphone. You can text and you can take pictures, you can read your email, but if someone says, but what's going on inside when that happens? We're like, yeah, I don't know. That's what Feynman means when he says we don't truly understand quantum mechanics. And the weird thing is, not only do we not try to understand quantum mechanics, we actively discourage it. There was a time back in the 1920s and 30s when it was thought to be a very high priority thing to try to understand quantum mechanics. And given how central quantum mechanics is to modern physics, you would think that the attempts to understand quantum mechanics would constitute the highest status subdiscipline within physics, right? The people who are best at trying to understand quantum mechanics would be the superstars of physics. They would be stolen away by major universities, lured with huge salaries. Instead, they are kicked out. Graduate students are told not to do this, and people who already have tenure, when they say that they're trying to think about quantum mechanics in a deep way, their colleagues go, it's too bad that you've left serious work behind. So in other words, the way I like to think about it, there's this old fable, one of Aesop's fables about the fox and the grapes, right? The fox sees the grapes, big juicy grapes, they look really good. The fox jumps up to get the grapes, but they're just too high. The fox just can't quite reach the grapes. So the fox says, you know what? I never wanted those grapes in the first place. They were probably sour. So just to spell out the terms of the metaphor, the fox represents physicists. The grapes represent understanding quantum mechanics. We tried for a while. It didn't work, so we've decided we never wanted to do it in the first place. That wasn't our job. I think that's wrong. I think that it is the job of physics to understand the nature of reality, and even though it sounds a little philosophical, we should still put some effort into it. So let me see how far we can get. So I do need to tell you a little bit about quantum mechanics. Again, it's at the center of all we do in modern physics. It's absolutely part of our best understanding of reality, but it is absolutely counterintuitive. So I don't want to say it's mysterious or spooky or impossible to understand, but it does seem weird from our everyday experience. So let me just trace through like a very rationalized, simple version of why we came to believe the weirdness of quantum mechanics. You've all seen pictures like this. This is the Rutherford atom. This was the picture of the atom that was put together in the very beginning of the 20th century, where rather than an atom being sort of a smooth sort of blob of stuff, it actually has almost all the mass concentrated in the center in something called the nucleus. We now know the nucleus of an atom is made of protons and neutrons. They weren't sure about that in 1909, but they knew there was a nucleus. And the electron, which is much lighter than the protons and neutrons, the electrons orbit around. And in a picture like this, it kind of looks like a little solar system, right? With the nucleus playing the role of the sun, and the electrons kind of look like planets. This was what was forced on us by the data. Rutherford shot little helium nuclei at gold, and he noticed that usually they went right through, but sometimes they careened off at crazy angles. He deduced, because he was very smart, that that meant there was a concentrated set of mass in the middle called the nucleus. The problem is, this can't be right. The rules of physics as we understood them in 1909 are something called classical mechanics, put together by Isaac Newton in the 1600s. And according to classical mechanics, there are objects, they have locations, and they have velocities, and from knowing that, you can figure out everything that's going to happen in a physical system. So you apply the rules of classical mechanics to this atom. So you see those electrons orbiting around, right, very, very quickly around the nucleus. Well, if you take an electron, the thing about an electron is it has an electric field stretching out away from it. And if you move the electron a little bit, the field shifts in response. So if you take that electron and move it up and down, the electric field waves, it ripples out. We call these electromagnetic waves or light. Literally all of the light that you see in this room right now comes from electrons moving up and down. Here you have some electrons moving up and down. Maybe they move in circles, but they're still moving. They should be giving off light. They should be giving off electromagnetic waves. You can calculate how much they should be giving off. You can assign this to your undergraduates if you want to do that. It doesn't take long for the electrons, according to this theory, to lose energy by giving off light. Energy is conserved. The electrons give off light. They should be spiraling into the nucleus. The orbit of an electron around a nucleus is not stable, according to the rules of classical mechanics. And your undergraduates will get the answer. It takes about 10 to the minus 11 seconds for an electron in a typical atom to spiral into the nucleus. That is a very short period of time. So we can do the experiment. Ready? It didn't work. It didn't happen. Atoms are actually stable. If classical mechanics and the Rutherford atom were correct, this podium would instantly collapse down to a point. That doesn't happen, so there's something going wrong. And the thing I'm trying to get to you is that we really struggled with all this stuff before we came up with quantum mechanics. It didn't just pop out like Venus from the brow of Zeus, right? We were forced to invent these particular ideas. So at the same time, people had noticed that light, which I just told you was a wave, sometimes had particle-like properties. So they said, well, here's an electron, a particle. Maybe the electron has wave-like properties. And that actually worked. If you say that the electron is not a particle, if you say the electron is actually a wave, which physicists, they did not waste their brain power coming up with this name. They dubbed this wave the wave function. If you think that the electron is a wave function that can take on different shapes, then that wave function can settle into one of these shapes. Here are some of the shapes that an electron can have orbiting a nucleus, and it will just stay there forever. It will not spiral in to the center. So you can explain why atoms are stable if you make the bold leap, and it took years to get there, right? But we did eventually get there. If you make the bold leap that electrons are not particles, they're actually waves. That sounded pretty good, but physicists are not really happy until you have an equation, and I know that we're having the quiz afterward in which you'll be able to solve this equation, but this is the equation that came along soon thereafter that tell you how wave functions evolve. So the state of the art here is we're imagining that subatomic particles like electrons are really not particles at all, they're waves. And they obey an equation, okay? You don't need to know the details of the equation. Psi, that capital Greek letter, that's the wave function. And here's Erwin Schrodinger, who says this is the equation that tells us how wave functions behave, how they evolve over time. Solutions to that equation would give you all of these different pictures for different shapes the electron wave function could have in an atom, for example. And you could use this equation, you could make predictions for how electrons could give off light under certain circumstances, but then they could settle down to their minimum energy state. This makes physicists very happy. When you have an equation, you have full employment. You can not only solve the equation yourself, you have an infinite number of homework problems to give to your students in the future. And to this day, many quantum mechanics classes are basically solving the Schrodinger equation over and over again. It's quantitative and rigorous and definite. It says what's going to happen next. This is definitely physicists' comfort zone. The discomfort comes when you realize that this equation by itself does not seem to fit our experimental data. Let me show you some data. This is a little qualitative, not quantitative, but this is a little tiny chunk of radioactive uranium inside of a cloud chamber. So when the uranium emits a particle, because it's radioactive, this is a chamber where a charged particle will make some ions which show up, okay? So what you're seeing are these little streaks when a particle is emitted from the uranium. That makes perfect sense. Radioactivity is particles coming out of the uranium. Very good. The problem is, when you ask the Schrodinger equation, what kind of wave function is emitted when uranium emits a particle, an electron, let's say, the answer is it comes out in more or less a spherical distribution. It comes out more or less in a big blob that gets more and more dispersed as it leaves the center of the uranium. That is not at all what we're seeing here. What we're seeing here are individual tracks, little trajectories, as if the electron was a particle again. So it seems naively, if you're really at the very dumbest level, what you would say is, it seems like electrons act like waves when you're not looking at them, and they act like particles when you are looking at them. So clearly, we should bring the brightest minds in all of theoretical physics to bear on this question and figure out what's really going on. And the answer they came up with is, electrons act like waves when you're not looking at them, and they act like particles when you are looking at them. So this is called the Copenhagen interpretation of quantum mechanics. This is what we teach our undergraduates in textbooks. What it says is that an electron wave function might be all spread out in some particular way when you're not looking at it, when it's there in an atom, for example. But when you measure something about it, when you look at it, when you observe it, the wave function collapses. You don't see that big spread out puffy wave of wave function. You see what looks like a particle, a wave function localized in some particular place. And where it's going to appear, you can't say for sure. This is where the probability comes into quantum mechanics. The wave function is basically telling you how likely it is that you will get certain observational outcomes. Where the wave function is big, it is probable to see the electron there were you to look. And where the wave function is small, it is improbable, but there still might be some chance. So this is codified in textbooks. I am not making this up. This is what we teach our students. We say, when you're not looking at a quantum system, it's kind of like classical mechanics. There are states of the physical system, and they evolve according to some equation. Except instead of the states being positions and velocities, they're wave functions. And instead of the equation being Newton's laws of physics, they're the Schrodinger equation. And that would be fine, but then there's this whole new set of rules for what happens when quantum systems are measured, when you look at them. Then the wave function collapses, and there's a probability of getting different outcomes. This is what is called the Copenhagen or textbook interpretation. So to drive this home, let's turn to the thought experiment stylings of Erwin Schrödinger, who did a famous, he came up with a famous scenario. Actually, he came up with this in correspondence with Einstein, but it was Schrödinger who actually did this experiment where there's a cat in a box, and the point of the experiment is to amplify the quantum wave function to macroscopic scales, okay? So the idea is you have a quantum mechanical source like that uranium I showed you, and there's a detector like a Geiger counter, and the wave function says the following thing, that there's some probability that the Geiger counter will click, and if that happens, it opens up a box of gas, which is released into the bigger box with the cat in it, and if it doesn't, then it's closed. So in Schrödinger's original equation, thought experiment, inside the box, it was cyanide gas, and that's, well, Schrödinger's daughter put it best. She said, I think my father just didn't like cats. So the cat's quantum wave function evolves into a superposition of being alive or dead, okay? There's no reason to kill the cat in terms of understanding the physics behind what's going on. So in my version of the experiment, I put sleeping gas inside the box, and the cat is in a superposition of being awake and asleep. All the physics consequences are just as good. Now, Schrodinger's cat was not invented by Schrodinger so that people could say, wow, you know, that's really bizarre and weird and amazing. Isn't quantum mechanics something else? It was invented because Schrodinger wanted you to say, surely you don't believe that. Schrodinger invented Schrodinger's equation, but he did not invent the interpretation of that equation, which says that what the equation is telling us is the probability of getting something. Because the point of Schrodinger's cat is, when you don't have the box open, you're supposed to believe that the cat is literally in a superposition. It's not true that it is either alive or dead, but we don't know which. It's neither awake nor asleep. It is a superposition of both at the same time until you open the box and look, according to the traditional interpretation. So the whole point of, you know, what does it mean to make an observation was left a little bit vague in this original interpretation. So in other words, we have a classical possibility. It can always be true that there's something we don't know, right? We can have a box with a cat in it that is either awake or asleep, and we're just not sure. That's certainly a perfectly respectable introduction of probability into physics. That's based on our subjective ignorance of the situation. But the quantum mechanical situation is different. The prediction of Schrodinger's equation is crystal clear, that in that box there is a superposition of both an awake and asleep cat. So let me tell you what happens when you open the box according to the Copenhagen interpretation. The point of Copenhagen is we treat small systems by the rules of quantum mechanics and big systems by the rules of classical mechanics. There is a dividing line between the quantum realm and the classical realm. This is called the Heisenberg cut, because not only Niels Bohr, who is one of the founders of the Copenhagen interpretation, but also his acolytes like Werner Heisenberg and Wolfgang Pauli helped develop these ideas. The Heisenberg cut separates the quantum world from the classical world. So you have a quantum mechanical cat, in this case, in a superposition of awake and asleep, and a classical observer. In this case, the role of the observer is played by Niels Bohr. And what the interpretation tells you is that when the observer opens the box, you either get a cat that was awake and the observer saw it awake, or the cat is asleep and the observer saw it asleep, and you don't know which. All you can do is predict the probabilities. The wave function is collapsed onto one possibility or the other. So the problem with this is that it is clearly rubbish. This is absolutely unacceptable as a fundamental theory of nature. Let me just mention two problems with it. So obviously it's a step along the way. I'm not telling you that quantum mechanics is false or wrong, but it just doesn't seem done yet. So the two problems I have in mind are one which we could call the reality problem, right? I said the electron should be thought of as a wave function. But then when you look at the electron, it doesn't look like a wave function. So the reality problem is, what is the wave function? Or for that matter, what is reality? Is the wave function itself a one-to-one isomorphic representation of what is really going on? Or is it somehow just encoding our inability to predict what the observational outcome is going to be? Are there other variables over and above the wave function? People like Einstein and others thought that there were hidden variables that could help us make predictions if only we knew what they were. Or does the wave function have nothing to do with reality at all? Is it just a tool for making predictions? None of these is answered by the traditional interpretation. And then even more famously, we have the measurement problem. Of course, I said, to make it vivid, I said electrons act differently when you look at them. And you should be thinking, what do you mean, look at them? Does it have to be a person looking? Does a person have to be awake? Could it be the cat looking at itself? What about a video camera? What about a rock? What if I just glance at it? You know, does that count? Does the wave function collapse when I just glance at it? Does human consciousness somehow get involved in this game? Does an agency and the ability to make observations and perceptions somehow matter to the fundamental rules of nature? So we don't agree. This is why there's a reality, a truth to Feynman's statement that physicists don't understand quantum mechanics, because Even though some people have some opinions on these questions, we do not have a consensus within the field about how to answer them. So my main message, if I have one, is that these are answerable questions. These are not impossible. It's not just philosophy. It's not just something you do if you're too tired to do real work anymore. This should be the job of physics to answer these questions. But my secondary message is, I think I know what the answer is. And it wasn't invented by me. It was invented by this guy, Hugh Everett, who was a graduate student in the 1950s working under John Wheeler. And basically, Everett's suggestion is that we should all just chill out. He suggested the simplest, most austere, most pure version of quantum mechanics. He said, you want to know what's real? It's the wave function. It's obviously the wave function. What else would it be? He says, you want to know how wave functions evolve? They obey the Schrodinger equation. You know that that's what they do. They don't do anything else. It's kind of a quantum therapy that he's offering people. So in other words, here is the Everett interpretation of quantum mechanics. There is only one set of rules. They always apply all the time. Systems are described by wave functions, and wave functions obey the Schrodinger equation. Okay? The problem is, I already told you what the problem is, that when you look at quantum mechanical systems like particles being emitted from radioactive substances, they don't look like wave functions. They don't look like they're obeying the Schrodinger equation. And Everett says that's because you need to think harder about what you mean by looking at something. And when you're doing that, you have to take quantum mechanics seriously. Taking quantum mechanics seriously to Everett means two things. Number one, you can't pretend that you're classical. You can't pretend that even though you're a big macroscopic observer, somehow you're free from obeying the rules of quantum mechanics. You're just as quantum as anything else. You're made of atoms. So you should obey the Schrodinger equation also. You should have a wave function. If electrons can be in superpositions of possibilities, you can be in superpositions of possibilities. That's one fact. The other fact is this idea that Einstein and others developed in the 1930s called entanglement. This is really what makes quantum mechanics special and interesting, is this phenomenon of entanglement. So I'm going to introduce it by a modern example, but there were examples way back in the day. We recently, in 2012, discovered the Higgs boson particle, right? A new fundamental particle of nature, the last piece that we needed of the standard model of particle physics we discovered at the Large Hadron Collider in Geneva. And a Higgs boson is special because of all the known elementary particles, it has zero spin. Elementary particles can spin just like the Earth spins around its axis, but at the particle level, individual particles have specified amounts of spin that are very definite numbers. So something like an electron or a quark can either spin clockwise or counterclockwise. As physicists say, spin up or spin down. But a Higgs boson has exactly zero spin. And the important thing about spin is it's conserved. It's not created or destroyed. The total amount is preserved. So when a Higgs boson decays into two particles, like let's say an electron and a positron, an anti-electron, or a quark and an anti-quark, a spinless particle is decaying into two spinning particles. But the total spin has to be conserved. So what you know is that the two particles that it decays into better be spinning in opposite directions. You don't know whether this one is spin up and this one is down, or vice versa, but you know they're opposite, so the total spin adds to zero, because that's what it started from. So quantum mechanics says you don't know what the spin of the first particle is going to be. It could be spin up or spin down. But you know that there's a relationship between the spin of that one and the spin of the other one. So the wave function of the Higgs boson, once it decays, is into a superposition of particle 1 is spin up, and particle 2 is spin down, particle 1 is spin down, and particle 2 is spin up. If you were to observe the spin of particle 1, you don't know what answer you're going to get. It could be spin up or spin down. If you observe the spin of particle 2, you don't know what answer you're going to get. It could be spin down or spin up. But if you observe the spin of one of them, and let's say you observe spin 1, particle 1 has spin up, then you know what particle 2 is going to be. It has to be the opposite to balance out. That is quantum entanglement. You don't know, there's no definite fact of the matter about the spin of either one of the particles, but there's a relationship between them. And this is a feature of the fact that there's a deep, deep feature of quantum mechanics which really makes it different than classical mechanics. In classical mechanics, if you have two particles, particle 1's doing something, particle 2's doing something else. There's a state of particle 1, its position and its velocity and its spin. And there's a state of particle 2, its position and its velocity and its spin. You might think that in quantum mechanics, every particle has a wave function. And sometimes we even talk that way. So particle 1 could have a wave function that's a superposition of spin up and spin down, and likewise for particle 2. But no, that is not how quantum mechanics works. There is only one wave function for all the particles at once. There is only the wave function of the universe. And in this case, the wave function of the universe is this particular entangled superposition. Okay? This is probably, for the first 2/3 of the talk, this is the deepest concept I'm going to lay on you. So you got to understand this, entanglement. You don't know what particle 1 is doing or particle 2, but if you were to measure 1, then you know what you would get if you were to measure 2. So let's apply this idea of entanglement and the idea that you yourself are a quantum system to the Schrodinger's cat experiment. That's what Hugh Everett suggests that we do. And there's no special role played by observation or measurement or consciousness. You're just a physical system obeying the laws of nature, okay? So you have the cat. It is in a superposition of awake and asleep. And you have the observer, now played in that role by Hugh Everett. And the idea of measurement is you open the box and you solve the Schrodinger equation. And the Schrodinger equation describes the cat, but it also describes you. So there's, again, absolutely no ambiguity about what the Schrodinger equation predicts. Before, in the Copenhagen interpretation, we made up a rule that says when you open the box and observe it, it collapses, and you see one outcome or the other. Everett says, just do what the Schrodinger equation says. And the answer is that you and the cat evolved to an entangled superposition of the cat was awake and you saw it awake, plus the cat was asleep and you saw it asleep. Again, no one doubts that that is what the Schrodinger equation predicts. The puzzle is, it seems like you are now in a superposition of having seen the cat awake and having seen the cat asleep, right? But no one ever feels like they're in a superposition. No one ever opens a box and says, well, part of me thinks the cat's awake and part of me sees the cat's asleep. No, that's not what you think. So it's not crazy to think that Everett was crazy. It sounds like what he's saying is obviously wrong. And in fact, in some sense, he was ahead of his time, because the solution to this puzzle really wasn't well understood until the 70s or 80s, with the idea that we now call decoherence. Remember, I already told you that there's only one wave function for the entire universe all at once. But then I showed you a little picture on the last slide with the wave function of the cat and the observer. So what about the rest of the entire universe, right? I really should include the rest of the entire universe if I'm not cheating you. So we bundle up the entire rest of the universe. We don't keep track of everything. We call it the environment, represented here by some leaves of grass. But the environment could just be the photons or the air molecules bouncing around in the room. All of the things, all of the particles, all the degrees of freedom that we don't keep track of individually in our experiment. But you can tell if the environment is the air molecules or the photons in the box, they interact with the cat long before we open it, right? So that process is called decoherence, because the cat becomes entangled with the environment. If the cat's awake and over here, a certain photon might hit the cat and be absorbed, whereas if the cat were asleep, that photon just goes right on by. The way that the environment interacts with the cat depends on whether it's awake or asleep. So the cat very, very quickly becomes entangled with the environment, and that process is called decoherence. The observer just goes along for the ride until then they open the box, and then they become entangled with both the cat and the environment, okay? This story I just told you is just a slightly more accurate version of the story I told you on the last slide. So why am I bothering to tell you this slightly more accurate story? Because you can show, using math and stuff like that, that this state of the environment, entangled with the cat, is perpendicular to this environment entangled with the sleeping cat. And what that means is that what happens in the future in this part of the wave function is never affected in any way by what's going on in this part. They have become uncommunicative. You know, they do not talk to each other, they do not interact, they do not influence each other anymore. That's what decoherence really is about. And that's what measurement is, according to the Everettian version of quantum mechanics. Measurement is simply when a small quantum system becomes entangled with its environment. And what happens then is the wave function is a superposition, but the different parts of the superposition go their own way. What happens in one is independent of what happens to the other. They branch, as Everett put it. They split into two possibilities. It is as if those two parts of the wave function describe separate independent worlds. And that is why the Everett interpretation has been dubbed the many worlds interpretation of quantum mechanics, because these two parts of the wave function, here and here, don't talk to each other anymore. We should treat them as if they have nothing to do with each other, as if they are independent. So what I want to emphasize is I didn't put in a bunch of worlds. All I did was take the Schrodinger equation seriously. The Schrodinger equation predicts the existence of many worlds. Every other version of quantum mechanics is a get rid of the other worlds interpretation, okay? And maybe that's worth doing, but Everett says, why bother? He says what happens when I just obey the Schrodinger equation is what was one copy of me is now two copies of me in the future, but they're separate people. They don't have any way to talk to each other or anything like that. Just take them at face value. There's two different worlds. That's it. Live with it. Chill out. Don't mess with the rules of quantum mechanics. People don't like this. It did not go over well. Everett's thesis advisor, John Wheeler, was another acolyte of Niels Bohr, the grand poobah of the Copenhagen interpretation, and many harsh letters were sent back and forth over the Atlantic Ocean. Let's just put it that way. Everett never even tried to get an academic job. He left to do defense consulting, and the interpretation was more or less forgotten. But it's been rediscovered. So there are good reasons to be skeptical, or at least puzzles yet to be answered within the Everett interpretation. But there's also a bunch of not so good reasons to not like it. So I don't mind if you come away from the lecture at the end of the day not believing the Everett interpretation, but I want you to not believe it for the right reasons, if that's possible. So let me try to ask and answer some of the simplest questions about this. The simplest question, to which I only have a very unsatisfactory answer, is how many worlds are there anyway? I just showed you a picture where, with the cat, one world branched into two. But with an electron, if you measure the location of the electron, how many different possible answers could you get? The answer is infinity answers, right? There's an infinite number of points in space where the electron could be located. So naively, and maybe even in reality, there are infinitely many worlds. The reality is we don't know how many worlds there are in the many worlds interpretation of quantum mechanics. There could be infinitely many, in which case you shouldn't talk about how many there are. You should talk about the relative weight of worlds acting one way versus worlds acting in another way. What I want to get across is, it's not, people worry sometimes about, conservation of energy. If I measure a spin and suddenly there's two universes, where did all the energy come from for the stars and galaxies in that universe? But what's really happening is, as time goes up, you start with one big universe. There's a lot of weight. There's a lot of wave function attached to this single branch of the universe. And through a series of physical interactions governed by the Schrodinger equation, that universe is divided up into multiple copies. It's not that you're creating new stuff. The universes are, in a very rigorously, mathematically well-defined sense, thinner than they used to be because they're differentiating from each other. You're not creating more stuff, you're just differentiating the stuff that was already there into many, many, many copies. The people who are in the copies don't know this, but that's what the math says. So don't worry about conservation of energy or anything like that. Another question is, I just don't like it because there's too many universes. I don't want to, I don't want to disparage this kind of question too much, but I'm just trying to accurately capture the fact that really the reason why people don't like the many worlds interpretation is because it seems too extravagant, right? You're trying to answer a simple question about electrons and you end up inventing an infinite number of universes. Doesn't that seem like bringing an awful lot of ammunition to bear on a fairly small little puzzle? But I think that's exactly backwards. I think that Everett really is the simplest, most straightforward reading of quantum mechanics. Remember, all the many worlds interpretation is the statement that there are wave functions and they obey the Schrodinger equation. The worlds are a consequence of that. You did not put them in. If you believe that an electron can be in a superposition of spinning clockwise and spinning counterclockwise, and you believe that the world obeys the rules of quantum mechanics, then you can be in a superposition of having seen the electron do one thing and having seen the electron do other thing, and the universe can be in a superposition. You can't stop liking it when the superpositions become big unless you want to change the rules of quantum mechanics in some way. And you are very welcome to do that, but that makes the theory more complicated. It does not make it simpler. Everett is definitely the simplest way to go. The other easily answered objection is that this can't be tested. You've made a lot of worlds, and you've already said that I cannot influence them in any way or be influenced by them in any way. That doesn't sound like science to me if I can't get there. But that's not right. Every theory makes predictions that can't be tested. We don't count it against a theory when it makes some predictions that can't be tested. We ask, what are the predictions that can be tested, and we test them, right? The typical criterion we like to use, it's not perfect, but it's pretty good, is falsifiability. Can we imagine an experiment that would tell us that this theory, if you got the right answer in the experiment, that would tell us that this theory is not correct, that it is falsified? And in the case of Everettian quantum mechanics, the only posits are wave functions and the Schrodinger equation. Could you imagine experiments that falsify those assumptions? Yes, they're being done. It's going on right now. All you have to do is observe an isolated quantum system violate the Schrodinger equation. There are theories in which that happens, and they are being experimentally tested right now. Everett is the most falsifiable theory ever invented. It just hasn't been falsified yet. All right. The other thing I want to say is that I mentioned before, it's not just philosophy. I don't want to denigrate philosophy. I'm a big fan of philosophy. I think that philosophy is important, and certainly empirically over the last several decades, philosophers of physics have done a much better job at taking quantum mechanics seriously than physicists have. But I do think that maybe we shouldn't be surprised that we're struggling with certain puzzles within physics if we have abandoned the quest to understand quantum mechanics for its own sake. If you claim, if someone like Richard Feynman can get up in front of the room and say, I don't think anyone understands quantum mechanics, and then someone else comes up and says, well, we don't understand the quantum theory of gravity, for example. Well, why should we understand quantum gravity if we don't understand quantum mechanics, right? This is not usually the way people think, because we tend to start with a classical theory and then quantize it. So the search for something like quantum gravity is starting with the right classical theory of gravity and then turning it into a quantum theory. But presumably nature doesn't do that. Nature doesn't start with a classical theory and then quantize it. Nature just is quantum from the start. Maybe the reason we don't understand quantum gravity is because we don't understand quantum mechanics. And I suggest this not only as a logical possibility, because I think it might actually be true. So just to remind you of how gravity works, for those of you who have not read my textbook on general relativity, our best current theory of gravity is Einstein's theory of general relativity. The motto for general relativity is, gravity is the curvature of space-time. So you have to believe that there's something called space-time, the three-dimensional space all around us, plus time evolving us forward. Einstein says you should think of space-time not merely as the background, as the stage on which physics happens. It's a player in the game in its own right. Space-time is dynamical. It warps, it bends, it changes in response to stuff in the universe, to matter, to momentum, to energy is the simplest way of thinking about it. When an apple falls from a tree, It's because the energy of the Earth has warped the space and time around it so that falling is the simplest thing that the apple can do. So if you want the motto for general relativity, it's that geometry of space-time is somehow related to energy. This is the thing that we would like to get out of a quantum mechanical description of nature. So as I already said, we don't understand quantum mechanics, we don't understand quantum gravity. Maybe these lacks of understanding are somehow related. And so the program is, rather than quantizing gravity, we should find gravity within quantum mechanics. We should start with a purely quantum idea, which, by the way, this is the point of doing Everettian quantum mechanics. In all other, remember I said there are alternatives to Everett. There are versions where there are hidden variables, there are versions where the Schrodinger equation is violated. In all of these, some lingering element of classical reality is put in by hand at the start. There are some classical presuppositions that come into how we get rid of all those other worlds. Everett is the most purely quantum of all the approaches to quantum mechanics there are. So if you want to play the game of starting with a purely quantum description of nature and seeing how the classical limit arises, playing it within the framework of Everettian quantum mechanics is the most natural thing to do. So that's what we're going to try to do. Not to quantize gravity, but to find gravity, curved space-time responding to matter and energy within quantum mechanics. We are allowed to take hints from the real world. The best theory we have of the real world that doesn't include gravity is something called quantum field theory. You know, I talked about particles like electrons and quarks. That's a bit of a fake. In modern physics, the fundamental ingredients of nature are not particles at all, they are fields. And it's a very subtle thing to talk about because I already told you that electrons aren't really particles, they're waves. But now I'm telling you that the thing that is quantum isn't even the particle. It's not you go from particle to wave function. It's you go from wave, from a field, to a wave function of the field. And this is very complicated, and I wrote many words about it, and I put them in my book, and my editor told them to delete them because no one would understand what I was talking about. But it is the final answer. Like, at the end of the day, this is how things work. For the purposes of this lecture, you'll just have to trust me on this. The point of fields versus particles is, a particle has a location in space. It is there, it is not anywhere else. A field is the opposite. A field is everywhere. The magnetic field that you might see because you have iron filings spread around a magnet, there's the value of the magnetic field of the universe at every point in space. It might be zero some places, it might be large other places, but fields exist everywhere. And in quantum field theory, which is the basis of the standard model of particle physics, the quantum vibrations of those fields are what you and I perceive of as particles. And what that means is that even empty space has stuff going on. This is a foundational, fundamental, really important feature of quantum field theory that is glossed over most of the times people talk about it because we jump right to the particles. In quantum field theory, there are these waves that exist all over the place. They're all quantized waves, and they have a lowest energy state. And to you and me, that lowest energy state that we perceive as simply empty space, as if there's nothing going on. A particle happens when you take that little quantum field and you vibrate it strongly, right? More strongly than it would in its lowest energy state. We perceive that as a particle. If the world were really made of particles, we would say there's particles at some places and empty space elsewhere. If the world is made of quantum fields, we have some vibrating modes which we call particles, but there's still modes, vibrations of the quantum fields even in empty space itself. You will not be surprised to learn that these little patches of vibrating fields are entangled with each other. All the fields are vibrating, and of course, if they're right next to each other, if they had nothing to do with each other, no relationship, there would be a lot of energy contained there. So the lowest energy thing to do, the quiescent empty space state of the quantum field, is one where nearby patches of space are highly entangled. And regions of space that are very, very far away are not very entangled. So it is very natural that in quantum field theory, as we understand it, there's a relationship between the geometry of space because that's what you talk about when you talk about distances and triangles and lengths and stuff like that, and the amount of entanglement between those different regions of space. The shorter the distance, the more the entanglement. So let's turn this around. So that was taking a clue from what we already know about the universe. But our project is not to take some fields and quantize them. Our project is to take something intrinsically quantum and find the stuff we know within it. So instead of saying when things are close together, they are probably highly entangled, maybe what we can say is when things are highly entangled, let's define that to be close together. When things, and I'm using the word things because there's some more math involved in figuring out what the fundamental ingredients of this kind of description are, but when fundamental quantum degrees of freedom are not very entangled, then they're far away from each other. So in other words, if you give me a bunch of quantum stuff and you tell me how it's entangled, that knits them together, and if we're lucky, it knits them together to define a space, three-dimensional space, with a certain geometry that you can extract from the entanglement. There's a very natural relationship between geometry and entanglement. There is also a very natural relationship between entanglement and energy. Remember, we said that in empty space, the lowest energy state, things are entangled in a very, very specific way. And we also said that particles, which carry energy, particles require that you do something extra to the quantum fields in one region of space. And that extra thing you do, generically, breaks the entanglement between that little extra vibration that you perceive as a particle and the degrees of freedom around it. So when you put particles, and therefore energy, into a region of space, it becomes less entangled with all of the stuff around it. So there's another direct relationship between entanglement and energy. Adding particles decreases entanglement. So what do we get out of this bunch of hand waving? There's some equations attached to this, but let me be very honest. This is all very speculative stuff. I'm letting you in on the cutting edge, by which I mean stuff no one agrees with, except for me and my students. What we have is that it is very natural for entanglement to be related to geometry. What we know from quantum field theory is that the degrees of freedom in empty space are more entangled when they're nearby. So we could, in principle, extract the geometry of space from knowing the entanglement between everything in the world. There's also a very natural relationship between entanglement and energy. When you change the entanglement, or you break the entanglement between some degrees of freedom and some other ones, it's like putting energy in there. Thus, there is a relationship between geometry and energy, not starting from a description of space-time and fields and stuff, just from starting with a quantum wave function with different bits of it entangled in the right way. If you started with that quantum description and tried to say, what classical thing does it naturally correspond to, the answer is a space with a geometry where the geometry is related to the energy inside. But guess what? That's general relativity. That is the rules of space and time and gravity that Einstein invented back in 1915. So what Einstein had to do was posit an equation relating the energy in space-time to the amount of curvature. What we're able to do, under a long laundry list of assumptions that are kind of not yet proven, let's put it politely, they're not yet proven to be correct, but under some reasonable sounding assumptions, we can derive Einstein's equation from the entanglement of quantum degrees of freedom. So this is, again, very preliminary and work that is being done by certain people, the relationship between entanglement and space-time and geometry and so forth. But we can at least see the vague outline of a program where, rather than quantizing some classical theory and calling that quantum gravity, we take quantum mechanics seriously. There's wave functions, they're entangled, etc. And we ask after the fact, what is that quantum wave function? How would we interpret it? What is the classical limit? What is the emergent reality that comes out of that? And it's very natural, it seems, for that emergent reality to look like space-time obeying Einstein's equation of general relativity. So let me close with a quote from David Deutsch, who is one of the leaders of quantum theory in general and the many worlds interpretation in particular. He says, despite the unrivaled empirical success of quantum theory, by which he means the many worlds interpretation of quantum theory, the very suggestion that it may be literally true as a description of nature is still greeted with cynicism, incomprehension, and even anger. So I'm hoping that at the end of today's talk, at the very least, the incomprehension will be a little bit less than it was at the beginning. Thank you very much. And I think that there's time for questions, and I believe that I'm in charge. So what you will do is run pell-mell up to these microphones right here, and get in line, and I will pick on you. I don't know if are there any microphones up there? No. Sorry. But you're welcome to come down. All right, you are first.
Hi, Sean. Thanks for the great talk.
Thanks.
So in the Copenhagen interpretation of quantum mechanics, you spoke about two issues, one of which was the observer issue, what counts as an observer, and when does that measurement get made. Isn't that still an issue in the Everettian interpretation of quantum mechanics? What constitutes an event in which a branching would occur?
Good. That's a great question because I know the answer. Measurement occurs when a quantum system becomes entangled with the outside world and leads to decoherence.
Okay.
That's it. To understand when a measurement happens in Everett, all you have to do is solve the Schrodinger equation. Now, to be a little bit more fair, okay, there's a question of emergence. There's a question of microscopic and macroscopic vocabularies in which to describe the world. If you thought you knew the wave function of the universe, if you were Stephen Hawking who knew the wave function of the universe, you don't need to talk about branches. You don't need to talk about subsystems. You have the wave function of the universe. Why aren't you rich? The answer is because the reality we perceive as subsystems of the universe is this emergent, higher level, incomplete thing, which is not the wave function of the universe. So there's the single hardest thing to do in the Everett version of quantum mechanics is not to write down what the formalism is to connect that formalism to our experience. So, of course, we have an idea of what constitutes a measurement, opening up the box, putting the electron in a cloud chamber or whatever, and there is some work to be done in attaching the formalism to that. In particular, showing that the worlds really do split and then not talk to each other, and also showing why there's a probability rule that is the wave function squared. So that's the ongoing research of the Everett program. In my view, it's all very doable stuff.
Thanks.
Sure. Yes.
So when you are saying, like, when you observe a particle, are you just saying it's an excited part of the quantum field and that, like, just because you're observing it doesn't mean that entanglement doesn't exist, it's just less entangled? Is that what you're saying?
I'm not sure what I'm saying there. So what I'm saying is, let me say something that I'm saying, and we'll see if it's the thing that you hope that I'm saying.
Okay.
When there's a particle, which, yes, we think of particles as really certain excitations in a quantum field, but that's kind of not especially germane for the question of observing. It could have been a particle, or it could have been a field that we quantized. The point is, the thing we're observing has a wave function. So when we make that observation of its position or velocity or whatever, we cannot predict with certainty what answer we will get ahead of time. That's the empirical fact. The Everettian explanation for that empirical fact is you become entangled with that thing you're observing. And all of the possible measurement outcomes are actualized, but they're actualized in different parts of that entangled superposition where you have different feelings about what you think you just measured.
Mm-hmm. Okay, thank you.
Close enough? Yeah, that's it. Better than I usually get. All right.
Hi. So I was reading your book, and I was trying to apply it to the delayed choice experiments.
The delayed choice quantum eraser, yes?
Yeah, specifically to that one. So in the normal delayed choice appears pretty clear, like when you reach either the which path measurement or not, you are going to have decoherence for that, and therefore they are not going to interfere, or they are going to interfere. Now, it's very confusing to understand what is happening on the delayed choice counter eraser, because the signal photon is hitting the screen before any of that which path or not which path is going to happen. So you have a pattern there that you cannot see, but you have a pattern of the photons that later are going to hit the which path, and the photons that you cannot see because you don't know which one are going to hit or not, but the pattern is there, and the branching has to happen there. So how you can branch there if you still don't know which ones are going to go which way?
Good. So I'm not going to be able to give a complete explanation here. This is a longer story. For those of you who are not reading Hanging Out of the Wrong Street Corners, there's something called the delayed choice quantum eraser experiment, where this idea that you make a measurement and what was a wave now looks like a particle seemingly is delayed. So you make the measurements of everything before you actually previously measured a particle. And so it sort of acts wave-like or particle-like depending on something you do after the experiment is over, which seems weird and almost as if signals went backward in time. I think that the idea that the standard popular level explanations of this experiment are all needlessly, intentionally making things difficult, and it all makes perfect sense in ordinary quantum mechanics without any signals going backward in time. And the basic trick is to fuss around with what you mean by making a measurement. In Copenhagen quantum mechanics, what you mean by making a measurement is left a little vague. In Everett, it's 100% clear you're just solving the Schrodinger equation. So I said a measurement occurs when a tiny quantum system becomes entangled with the world. Well, what if rather than entangling it with a billion photons, you just entangle it with one other electron? Then you can keep that electron. You can like shield it from the rest of the world, and you can unentangle it. So you could apparently do the observation, but then undo it and change the results that you get thereby. But all I will say about it, it is 100% completely compatible with the ordinary evolution of the Schrodinger equation forward in time.
Is there some paper or something?
Yeah, we got a long line, sorry. I did write a blog post about this where I did my explanation of it in detail.
Sorry, what?
I wrote a blog post about this, so you can look that up. It was another section that my editor forced me to cut from the book.
I was wondering if is the split like from zero, like one branch to two branches instantaneously, or does it like?
Yeah. No, it is not instantaneous. It takes about that long. It's very, very fast. So literally, there's something called the decoherence timescale. If a photon hits your eyeball, you can ask, how long does it take for that to decohere just because the eyeball is a warm, wet thing that is interacting with the environment? Very roughly, it's less than 10 to the minus 20 seconds. So it's not instantaneous, but it's really fast.
Thank you.
I've got a question about general relativity. A clock in space has a certain rate at which it moves. A clock in a gravity field has a slower rate relative to that clock in space. So a clock on Earth would go slower, correct so far? Yeah, roughly. Because it's closer to the center of that gravity well. If it goes into a hole in the Earth, it's even closer. But it's under less gravity because it's inside the Earth. So does it go slower or faster than the one on the surface?
Go slower.
Thank you.
Hi, Sean. Thanks for the great talk. I thought it was quite illuminating. My question is a bit related to causality. I think a couple of people touched it before me in the questions. So when you have this branching, the causality of it is because the observer decides, I'm going to open the box in the case of Schrodinger's cat experiment, I'm going to open the box or not. So how do you kind of incorporate causality into the structure or the Everettian model? And the second thing is, I know you kind of had David Chalmers on your podcast, and he has an interesting perspective on how he undertakes the problem of consciousness.
I think we get one question. Sorry. 'Cause
Yeah.
there's a long
So
line here.
the question is connected.
Okay.
So because causality is kind of connected in my view to consciousness to begin with, because who decides at the beginning, at the singularity of all the many worlds, who decides how do you branch out, or what are the branches that occur?
Yeah, so in my view of it, consciousness has nothing to do with anything. Consciousness is entirely epiphenomenal on the physical goings-on that are in the universe. So the only thing that ever happens in this view of the universe is that there's a wave function obeying the Schrodinger equation. And guess what? The Schrodinger equation is completely deterministic. There is a question, there's a good philosophy question about how you derive probabilities in our empirical reality, but the wave function itself is completely deterministic. So at the level of wave functions and branching, there's no such thing as decisions. There's no such thing as making a decision to open the box. You're just obeying the Schrodinger equation. And there's no such thing as causality. You're just obeying the Schrodinger equation. All of those are words that are useful at the emergent level of higher level things like you and me, but they're not there in the microphysics.
Okay.
So regarding the branching, you said two branches don't talk to each other. Does that mean they can't interfere?
Yes, that's exactly what it means.
So they can't interfere at all? That's,
Yeah.
Okay, that's a bummer. All right.
Yeah, sorry. Otherwise, there's a lot more science fiction stories that we could tell, yes.
Yeah, so quantum mechanics to me reminds me a bit of statistical mechanics because they both deal in probabilities. And from statistical mechanics standpoint, like if we're talking about the bulk properties of some space, for example, this room, the pressure and temperature doesn't really depend on where that particular molecule of oxygen is. So my question is, if that is indeed the case, how useful is the multi-world interpretation if all of those worlds, like if the bulk properties of all of those worlds are exactly the same?
Are exactly the same?
Yes.
I'm not sure that I exactly get the thrust of your question. The worlds are not exactly the same. They have different observational outcomes in them. The cat is awake in one world and the cat is asleep in the other world. The rest of the worlds are the same. But there's a huge difference between quantum mechanics and statistical mechanics because the wave function is ontological. It represents what reality is doing. The distribution function in classical mechanics is epistemic. It represents our knowledge of what is going on. So yes, there's something that's going on with all the positions and velocities. We just don't know. But the wave function is really reality in this picture.
Okay, thank you.
Sure.
Hi. So my question was about the many worlds theory. You mentioned here, right at the bottom of the page, think of splitting, not duplicating, to kind of talk about the conservation of energy that when you have, because you have this split and it's not a duplication, you don't end up with infinite energy, right?
Right.
But could you not work backwards with that argument and say that in order to have the splitting, you would either have to have an infinite initial universe or otherwise you would end up eventually to the point that the splitting has become so intense that you can no longer split? Or is there always going to be the availability to split? You know what I'm saying?
Yes, I know exactly what you're saying. Sorry, if I look distracted, I'm going to call a halt to more people getting in line. So 1, 2, 3, 4, 1, 2, 3, 4. 8 people get questions, because otherwise we'll be here all night, okay? Yes, so you're absolutely right. There is, as I believe, if there is a limit to how many times the wave function can branch, because there's only a finite number of possible branches, then you will reach a point at which branching is no longer possible. And that point is basically thermal equilibrium. That's the point where everything is smushed out. Cosmologically, it will look like we live in empty space, and there will be no such way, no sensible way of delineating different branches of the wave function. But we're just nowhere close to that right now, so that's a question for our ancestors. Ancestors? Descendants.
Thank you.
Physicists. Thank you. All right.
Okay, my question is about ADS CFT question. So you said that entanglement can relate the energy and the geometry of the spacetime, but the ADS spacetime, the boundary of the ADS spacetime locally looks like a Minkowski spacetime. So what if we choose the boundary of the black hole and infinite, like on the left and on the right, if we use the entanglement related the energy and the geometry, may we have a calculation on the quantum gravity over the boundary of the black hole?
Right. So I'm only going to give you a partial answer to that question because you've clearly been cheating on me and listening to other people other than me talk about quantum gravity. There's a thing, for those of you who don't know in the audience, there's something called ADS-CFT, a relationship between a cosmological space-time, where gravity is important, called ADS for anti-de Sitter space, and a particular kind of quantum field theory in one lower dimension called a conformal field theory, or a CFT. And they are the same theory, to some approximation, in very, very different guises. So we have a theory of quantum gravity that is the same as a theory without gravity at all. And naturally, this is a wonderful discovery by Juan Maldacena, a physicist at the Institute for Advanced Study. Much effort has gone into understanding things about gravity from understanding field theory and vice versa. In particular, what you can show, first I think mentioned by Mark van Romsdonk at UBC, the thing that gets you the curvature of space-time on the gravity side of the relationship is the entanglement of the fields in the quantum field theory side of the relationship. So there's a relationship between geometry and entanglement. That relationship is completely different from this relationship, even though this is also a relationship between geometry and entanglement. So ADS-CFT is an example where they're maximally far away, in some sense, from empty space. They're in a cosmology that is infinitely big, that is full of a negative energy density. And this holographic fact that things going on the boundary are reflected in the curvature inside is taking advantage of gravity really being different when gravity is strong or when space-time is big. So like a black hole or an ADS would be like that. Here, I'm working in the weak field limit very close to empty space. So my goal, this entanglement is not in a faraway boundary. This entanglement is right here in this room. Our goal here is to understand why apples fall from trees, not to understand a black hole in a five-dimensional space-time.
Okay, thank you.
Sure.
I feel like this is probably not a very good question, but what does it mean when things are entangled?
What does it mean when things are entangled? Good. Is that it?
Yes.
Okay. So the burden that you're struggling under is having grown up in a classical universe. So you think that if I have a particle, not you personally, but people think that if I have a particle, it has a location in space. That's a very natural, innocent sounding thing to think, right? In quantum mechanics, when you have this wave function, there's this way of talking that people have that says, the wave function tells me where the particle is when I look at it with certain probability. But what Everett is trying to tell us is, that's not right. The wave function doesn't tell you the probability of the particle being there. The wave function is all that exists. Before you looked at it, there's no such thing as where the particle is. There is only the wave function. So in what positions are in Everettian quantum mechanics are observational outcomes. They're not the fundamental ingredients out of which things are made. So if you have two particles, then you can ask, what are the possible observational outcomes if you were to observe the positions of both particles? Ordinarily, you would think, where are the particles? And I'm trying to train you to think, what are the possible observational outcomes? An entanglement is simply when the possible observational outcomes of one particle are related in some non-trivial way to the possible observational outcomes of the other particle. You can say, I don't know where this particle will be observed, but if I observe it here, then I can say something about the other particle. That is entanglement.
Okay, thank you.
So my question was touched on in your book, but just briefly, so I'm glad to have the opportunity. If I were to ask you, as a physicist, how you choose what to work on, which is one of the big questions a physicist has to answer, I'm sure you'd give a very interesting and cogent response, but it would be wrong, because there is no choice or free will in this many worlds theory, right? If you have a big enough computer and you set it going at t equals 0, you can predict everything. So if I'm an evil hacker with some ransomware to make $100 million, and I'm trying to decide whether to do it or not, And I could make two opinions. I could say, think about the future where I have done this awful deed. I'm looking back, but I really had no choice because there is no choice, so no big deal, let's do it. And number two, which I think is even worse, is I can say, well, one of my doppelgangers in these many, I have lots of doppelgangers splitting off all the time, all doing every possible thing. A lot of them are doing this awful thing, so why don't I do it and get the benefit in my branch? So my question is, why should anybody who believes in many worlds theory strive to live an ethical life?
Good. I mean, the short answer to that is read chapter 9 of my book, Something Deeply Hidden.
I have read chapter 9. I have.
But here is the longer answer. If you truly believe that you don't have the ability to make choices and affect the future, and everything that's going to happen to you is determined by the laws of physics, then I suggest that you implement this belief in your everyday life. So like when someone says, what do you want for dinner? You say, whatever the laws of physics have predicted, I will have for dinner, right? Do you love me? I don't know. Whatever the laws of physics say, I will say in this. I predict that you will not get very far in your life doing this, and I can explain why. It's because there are different vocabularies for talking about the world that obey different rules. There's a vocabulary for talking about the world that is fundamental and microscopic and reductionistic, where you have the wave function of the universe obeying the Schrodinger equation. And indeed, in that vocabulary, there's no such thing as choices or free will or options. It's deterministic. It does what it does. But there's another vocabulary for talking about the world where you have people and planets and puppies, and choices and opinions and desires and ethics. And in that vocabulary, things are not determined, because we have woefully incomplete information about the wave function of the universe, and you do have the ability to make choices. So I suggest that you take advantage of it.
Thank you.
I was just wondering if there was a, you said that so when the Schrodinger equation is completed, there's a splitting of the universe, and I was wondering if each, I guess, many separate world of the many worlds theory has like a predetermined weight, or is it all the same, things like that?
Yes, no. So, yes, no. The thickness of this diagram is supposed to sort of colorfully suggest the different weights that go into this. So very typically when we're given this example of, a spin that we're going to measure, is it spin up or spin down, we are often, given an example where the superposition is an equal weight between spin up and spin down, and you say there's a 50-50 chance. But it's very easy to prepare wave functions for spins where it's 1/3 likely to be spin up and 2/3 likely to be spin down. And that is a puzzle for Everettians who want to say where this probability comes from, because there's nothing truly random or stochastic. The only difference is that the weight is different. And I think that there are very good arguments as to why so basically I'll give you the 2-second answer. When the splitting happens, exactly because decoherence is very, very, very fast, the splitting always happens before you know it. So even though this person here can predict with 100% certainty that there will be a copy of them there and a copy of them there, once they're there, there will always be a moment of time when these two people don't know which branch they're on. And it turns out there's a uniquely sensible way to assign a credence to being on this branch or this branch, and it's a wave function squared.
Okay.
Yes, I hear mumbling. Go ahead.
I have a two-parter. So one, how do worlds split? And two, how does your answer, decoherence perhaps, avoid the same flaws or criticism of wave function collapse in the Copenhagen interpretation?
Good. So the question is, how do wave functions split? It is my answer is decoherence. Good. You predicted me correctly. The difference is that I have a very specific equation that tells me what happens at the microscopic level, the Schrodinger equation. It's exact. It's always obeyed in this picture. All else is commentary. The dividing up of the wave function into different branches, etc., is all convenient for we human beings in exactly the same way that it's convenient to divide this room, which is full of atoms and photons and so forth, into people and floors and stuff like that. It's a higher level approximate description. So there is no immediate moment when the wave function branches. It happens gradually over time. But when you solve the equation, the amount of time it takes is this really preposterously tiny number, like 10 to the minus 20 seconds. So the way to make that quantitative is to ask, how quickly do these two states, the environment that's entangled with the awake cat and the environment that's entangled with the asleep cat, how long does it take to make them go perpendicular? Okay? And that's a very quantitative question that you can ask, and the answer is very, very fast. And that's when the measurement happens. The measurement happens when the quantum system becomes entangled with the environment, and the two environment states that are entangled with the cat become perpendicular to each other.
Thanks.
Sure.
So suppose you had two entangled particles that were, I don't even know, like light years apart with the corresponding probability of them being there. And you measured one of them to be spin down, would you automatically know that the second one is spin up? And if so, wouldn't that violate the fact that information can't travel faster than the speed of light?
So yes, and depends. What you're suggesting is exactly the EPR puzzle. EPR being Einstein, Podolsky, and Rosen. This was one of Einstein's great contributions to quantum mechanics. There's a myth that Einstein was too old and curmudgeonly to really understand quantum mechanics. He understood it better than anybody else. He just wasn't happy with it. And this is one of the reasons why. Because if you have two entangled particles, you can move them as far apart as you want. You don't know what measurement outcome you're going to get. But when you measure one of them, you instantly know what the other one will be. The problem is that it's completely useless for sending signals, for communicating, because you've measured this one, but they don't know that you've measured it. They don't know what your answer is. You would have to send them the information about what your answer was, and you would send them in a signal moving at the speed of light, right? So there's actually a no signaling theorem in quantum mechanics that you can't use entanglement to send signals faster than the speed of light. So it seems like something kind of happens faster than the speed of light that miraculously cannot be used to send information. Should that bother you? It's up to you. I will not tell you to be bothered. All right, last question. Oh my goodness, the pressure is on you.
It's a really simple question now that I've heard all of these. But so you brought up a lot of really interesting topics. But if you could just sum up and help us understand the one topic, what do you want us walking away with truly understanding? What would it be?
Good, that's a great question, actually. And I think that I want it to be the thing I want you to take away, the thing I want you to remember 10 years from now, when people ask you about this talk, and you're like, oh yeah, that talk, sure. It's not any fact about quantum mechanics or even a fact about physics. It's the attitude that the job of physics is to understand reality. It's not just to make predictions. Physicists, post all the difficulties of quantum mechanics, have occasionally talked themselves into the idea that physics is not about reality. Physics is just about making predictions. I think that's a bad attitude, and I think that quantum mechanics is not magic, it's physics. And we should try to understand it, just like we should try to understand cosmology and what happened at the Big Bang and the relationship of physics to consciousness and all of those other things. That's our job, and we can do it as long as we try.
Thank you.
Thank you.